One of the most popular machine learning algorithms for predictive tasks is Random Forest. In this video, we will outline 3 different techniques for hyperparameter tuning with a Random Forest classifier. These will include grid search, randomized search, and Bayesian search. We'll work through examples of implementing each in Python and compare the results in terms of performance and computational speed. All coding shown in this video is done in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. So we can start by asking ourselves, what exactly do we mean by hyperparameter tuning? So let's just very briefly touch on this topic. With most machine learning algorithms, we will have 2 distinct sets of parameters that define how that algorithm is structured and how it will behave. So the first set are what we'll call model parameters. And these are numbers that are learned during the training or fit phase of the model. We have another set of parameters, and these are called hyperparameters. And these are usually associated more with the architecture of the model, how it's structured. And these cannot be learned during the training or fit phase. So we need another approach to learn or to optimally set what the values of these parameters should be. And so this is where hyperparameter tuning comes into play. We can consider hyperparameter tuning to be a type of meta-algorithm. So it's an algorithm that's on top of the algorithms that define our machine learning model. And so the 3 different approaches that we will cover here include grid search, and this is a very mechanical way of doing hyperparameter tuning. Essentially what we do in this scenario is we predetermine a set of values that each hyperparameter can take on. And we simply just iterate through all possible combinations. We train a model using these hyperparameters on a predefined training set, and then we look at the results. And we essentially just pick the model that has the best set of results. The second approach that we'll cover is called randomized search. And this is similar to grid search, except that we don't just mechanically cycle through all the different possible combinations. What we do is we just randomly select a subset of possible combinations of hyperparameters and then evaluate the model using these hyperparameters and just select out the best possible choice. One nice thing about randomized search is that instead of defining the possible parameters as a discrete set of possible values, we can use a probability distribution in order to define what the possible range of values can be. And the last technique that we'll explore here is called Bayesian search or Bayesian optimization. And in this case, it's similar to randomized search. We are only going to use a subset of the possible values for each hyperparameter. And we can define each hyperparameter as a probability distribution. In this case, though, Bayesian search also makes use of priors on each hyperparameter. So we can encode in the prior some knowledge, some intuition that we may have about what the hyperparameters should be. And we can encode that in there, and hopefully if we make guesses that are fairly correct or intuitive, that may speed along the hyperparameter tuning process. So for a random forest classifier, there are various different types of hyperparameters that we can choose from. On my blog, I have already written an article defining what a random forest is and how it is built. You can find a link to this blog article in the description below for those who are interested in deep diving into what a random forest is. But for the purpose of this video, we are going to limit ourselves to just 6 hyperparameters. Let's cover those now. So the first one is called the criterion. And this is simply the function that we are going to use in order to measure the quality of each split at every node in the constituent trees of the random forest. So typical values here can either be the Gini impurity or entropy. The next hyperparameter that we'll choose is the number of estimators. And so this is just the number of trees that make up our random forest ensemble. Next, we'll also look at the maximum depth that each tree can possibly take. We'll also look at the minimum number of samples at each node that will enable us to do a split on that node. So if we have less than this minimum value, then a split is not allowed, and that basically enforces that it would become a leaf node. The next hyperparameter is the minimum number of samples for a node to be considered a leaf node. So this is basically just setting a threshold for when we can stop our branching within each tree. And we will also set what the max features function is. And so this is just to determine which features will be used in each tree for when making a split at a particular node. Okay, so now we're in a Jupyter notebook, and as I mentioned previously, this notebook is available on my GitHub, and you can find the link to that in the description. So let's now work through our example with hyperparameter tuning. So the first thing we can do is run the first cell, and this just will import all the packages that we'll need later on. Okay, and now we will create our data set. And so this, we're just going to create a toy data set by making use of make classification that's available through scikit-learn. And the data we'll create will consist of 5,000 samples with 100 features, of which only 50 will actually be informative. Now, this will be a classification data set, and so our labels will consist of discrete values, and in this case, we will have 2 classes. The classes will have only a slight imbalance, so there'll be an imbalance between the 2 classes of 60 to 40%. And I'm also setting the random state to be equal to 42 so that we get reproducible results. Now, once we get our data, I'm also going to do a train test split where 20% of the data will be set aside for testing. So we can run this cell, and that will execute. And now I will also define just a simple helper function that will make it a bit easier, a bit more tidy later on when we're evaluating models. So let's just define that. So the first thing we'll do is define our baseline. And what we're aiming to do here is just to see how does the random forest classifier behave with all default values set for the hyperparameters. So this will serve us to just as a point of comparison with the results we get from all the various different types of hyperparameter tuning. Okay, that ran quick, and we have a set of results in terms of accuracy, precision, recall, F1 score, and the ROC, area under the curve. So now that we have our baseline in place, we can proceed with our first approach with hyperparameter tuning, and that is grid search. So what we're doing here now is we're going to define our set of parameters. And here we see that, we see what these values are. So for criterion, we're selecting options to be either Gini, entropy, or log loss. For number of estimators, we are selecting 50, 100, or 500. For maximum depth, we're allowing 1, 5, 10, or 15. Minimum sample splits, 2, 4, 6, and 8. Min samples for each leaf node can be 1, 2, 3, or 4. And then the determining the maximum number of features, we'll either use a square root or log base 2 functions. So this is how we're going to do our grid search. Let's kick this off right away. Okay, so we've jumped ahead in time. It's taken almost half an hour for grid search to finish. We can see that here with the listed wall time. But now it's done running, and we have also returned the set of hyperparameters that it has found to be the best for this particular problem. So now we can take our best estimator, and that's just returned here. So G is just the instance of our grid search object, and then if we just call the best estimator method, that basically returns the best model that was found from this search. So we can test it on our held out test set to see what kind of results we get. Okay, so here we've got an accuracy score of about 88, precision of 0.97, recall 0.73, and F1 score of 0.83. And we also have an area under the curve of about 0.97. So if we compare this to the baseline, we see that there's perhaps a modest improvement. The accuracy is about the same. The precision is a bit better with grid search. And if we look at the area under the curve is a bit higher with the results from grid search. So that's our first run with doing hyperparameter tuning. Now let's try some of the other methods. And the next one we'll try is randomized search. So in this case, what we have is the same parameter space. For the criterion, it remains unchanged from grid search. So we have the same values here. But now for the next 4 hyperparameters here, I'm defining them with distributions. So the number of estimators and the maximum depth, I'm defining them with Poisson distributions. And then the minimum samples split and minimum samples leaf are going to be determined with these random integer distributions, where I just define the minimum and maximum ranges that we can get. So now let's run this. Okay, and we can see right away that this proceeded a lot faster than grid search. In fact, it just took under 1 minute to complete. So here we have also returned the final set of hyperparameters, and we see that because we're using distributions for at least some of these hyperparameters, we're able to get quite a lot more resolution in terms of what possible values can be found. So we can print out the final results here. And here we see some improvements again. So we have an accuracy score of, accuracy and precision are quite a bit higher than what we saw with grid search. If we take a peek back, they're a bit higher. The recall score is about the same. The F1 score is a little bit higher. And actually, if we look at the area under the curve, we actually have a bit of a decrease for randomized search, which is kind of interesting. So now let's try out our final method, and that's going to be the Bayesian search or Bayesian optimization. So here again, we have the parameter space being defined with a set of distributions. Here, the way that it works with this implementation of Bayesian search is that we basically define what the type of each parameter is. So for example, for all the ones that we're considering here, they're integers. So we use this integer class here, and we define the possible range. So here I'm saying that n estimators can take on possible values between 50 and 1,000, and then I set my prior. So for the case of number of estimators and maximum depth, those are the first two distributions here, I'm saying that the prior will take a uniform distribution, so it can be equally as likely across the defined range here. For minimum samples split and minimum samples leaf, I've defined the ranges here as well, but I've changed the prior to be log uniform. And that's just to add extra weight to be placed towards the lower values of this range. And I'm simply doing that because if we look at the documentation, the default values for these two hyperparameters are set quite low. And so just my intuition is that that should be in the ballpark. It should be something roughly what we would expect to get as an output. Now the max features here and the criterion here cannot be defined as distributions because these are categorical hyperparameters. So we just leave them unchanged from the previous two examples. So now let's run this cell. Also, one last thing I'd like to point out is that the number of iterations that I'm considering here for the Bayesian search is the same as randomized search. So we're just going to run through 10 iterations, and that is just so for the point of comparison between the two, that it makes a little bit more sense. We're comparing apples and apples together. So let's run this cell. So okay, like for randomized search, this ran pretty quickly. The computation time was just over 1 minute, so it was about the same time as the randomized search. And we've also returned the set of hyperparameters. So what Bayesian search found is listed here. It's a little bit different than what we saw with randomized search. For example, if we look at the minimum sample leaf and minimum sample split, we see that the values here, it's both set at 2, is a bit lower than what we saw with randomized search. So if we go back up, randomized search found higher values at 4, and this is simply a result of our choice of priors. So remember the log uniform prior will put more weight towards lower values. Otherwise, though, these values are pretty consistent with what we've seen previously. So now if we print out the results, we get the following. And these look pretty good. So the area under the curve is higher than what we saw with randomized search. If we go back up, we have just a marginal increase over what we saw with randomized search. So we have something a little bit better here. The F1 score is still pretty good. It's about the same. And in fact, the other results are pretty much the same. The recall we have with Bayesian search is 0.74, and that's a little bit better than what we saw previously. So right, so we can kind of draw on some conclusions here. So out of all the different methods that we experimented with here, both Bayesian and randomized search take approximately about the same amount of time. The Bayesian method took a little bit longer, but it wasn't anything really dramatic. By far, the method that took the longest to compute was grid search. So grid search, if you remember, took about half an hour, so that's quite a bit longer. And as well, grid search didn't really return the most impressive results by far. By all appearances, it looks like our setup with Bayesian search yielded the best results overall, although they were not dramatically better than what we saw with randomized search. So both randomized search and Bayesian search were pretty good with this particular data set. As mentioned earlier, both randomized search and Bayesian search or Bayesian optimization both benefit from being able to handle distributions to define the possible values of hyperparameters, whereas grid search, we really can't do that. We have to hard code each possible value that we want to try out. So it's one nice little feature of randomized search and Bayesian search. And yeah, basically grid search really didn't perform all that well. As mentioned, it was pretty slow, and the values that we got out were somewhat better than the baseline, but overall it wasn't all that impressive. So if you enjoyed this video and learned something from it, please like, share, and subscribe to the channel. It's always appreciated. It's great to get your feedback. So until next time, have a great day and see you in the next video.